Hi guys, today I want to touch one little bit specific problem, which is intersection of two-dimensional polygons, and for that we can use OpenCascade library, because there is such an algorithm in OpenCascade. It's not exactly exposed in application programming interface of the library, but it exists, and why not to use it? So imagine that we have a couple of polygons which we want to intersect in two dimensions, like these polygons are planar, and we want to know if these two polygons intersect each other, and if yes, then what are the intersection points. For that purpose, we are going to use a tool which is located in the package Intf of OpenCascade, and I'm going to give it a try here in a dedicated lesson. If you do not know where to start, you can go to our repository of lessons. You can find that we have this repository here. You can find several lessons in there, and actually you can start from lesson 04, which contains not only a main function, but it also contains a couple of interaction facilities, so that we can have a 3D viewer in our lesson, or alternatively you can also just go and clone this lesson 13, which is exactly what we are going to do today. So you can just grab this complete solution from here. So we are going to start from this Intf interference polygon 2D tool, which is a class, which is an algorithm in OpenCascade. You can find it there. This is this class. It was developed back in 1992 by a French guy, Didier before. I mean, the interface of this tool is quite self-explanatory. You can just create an instance of this class here and initialize it with two polygons. So for those of you who wonder which library we need to plug in order to have this tool, let's do a quick research and try to find this Intf package. For that I am looking for a file having specific name, packages, and it should contain this intf string. So you can see that there is this tk geom algo in the source directory of OpenCascade, and in this folder, folder dedicated to a toolkit, because tk stands for a toolkit, we have a file named packages. And if I open this file, I will find that this toolkit, this file lists all the packages it is composed of. So you see that there is this intf package in there. So yeah, and tk geom algo, I think it is in the modeling algorithms, and you can find it in OpenCascade sources in tk geom algo. We can go and find this intf package. So here is the full contents of this package, and what we are interested in is actually this tool here, which is intf underscore interference polygon 2D. There is a number of other things, and if you go to intf.hxx, you will likely find some hint here saying that this package is intended at computation of interferences between polygons, lines, and polyhedra, but actually we are not going to use a lot from this package. We just need something to intersect our two-dimensional polylines. So let's go ahead and see how to use it. And you see that we have to initialize this tool with two polygons, and if I go there, if I check the definition of this thing here, I'll see that it's basically just an interface. It declares, this class declares a bunch of pure virtual functions, and it means that I cannot just construct instances of this class. I have to subclass it, and I have to provide my own implementation of what I would call a polygon 2D. So let's see how we can do that, and for that let's go back to our lesson. The first thing I need to do, I need to include this interference polygon 2D. So let me do this right here. And Okay, let me call it something like algo, and here I'm supposed to provide a couple of polygons, a couple of polylines which I want to intersect, and for that I need to have them in the first place, and for that I'm going to subclass this. What was it? It was Intf polygon 2D. Yeah. So I need to go ahead and declare some, I don't know, simple polygon, and let it subclass this intf polygon 2D. So here incomplete type is not allowed. It means that this class is declared with forward declaration in this interference polygon 2D, and to solve it I need to go ahead and include it explicitly here. Yeah, so here we go. What we are supposed to do, we are supposed to implement these unimplemented functions here. So you see that there are three functions, pure virtual functions. One of them is deflection over estimation, which is supposed to return the tolerance of the polygon for some reason. Then we have a number of segments in our polyline, and if we have just a straight line segment, it's going to be just one here. And as long as we might have several segments in our polyline, then we need to have an accessor by the index. So by this one based index, we are supposed to return two extremity points for the beginning of our segment and for the end of our segment. So let me just grab these three methods, and I'm going to implement them in the public section of my class here. So I'm not going to use this standard export macro, because what it is supposed to do, it's supposed to, for Windows environment, it's supposed to insert this decal spec DLL export and import instructions. So I'm not going to export anything, because I'm not developing a library, I'm developing an executable, and that's why I just go ahead and remove these two things. And for the rest, yeah, let's keep it like this. Maybe instead of standard real, I'd like to have just double, because it's a bit more explicit. And for standard integer, let's put just int. And yeah, so we are going to implement these three functions basically. And you can see that we are talking about two-dimensional polygon, because here we are supposed to return two-dimensional points in the first place. So now let me declare a constructor, because I want to construct my polygon from a series of two-dimensional points. So I'm going to declare it like this, and here I'm supposed to do something like this. So I'm going to enumerate all my two-dimensional points, like P0, then I don't know, P1, etc. And actually I want to simplify a bit this thing, and for that I'm going to use what is called in C++ initializer list. So for that I'm going to use this little bit strange thing, but it's really handy when it comes to, you know, when it comes to how you call your constructor, how you construct your object. So we have this initializer list, and it's going to contain just a pair of double values. I'll explain a bit later why it's so, but here I'm supposed to pass just poles, and here I need to do this, I need to provide some implementation. So why it is this tricky syntax here? So the idea is that in the main function over here I'm going to construct a couple of polygons. So let me call it like poly, I don't know, 0 and poly 1. So I'm going to have these two polygons, and here I want to use a syntax like curly braces, and then I just give the coordinates of my polygons, and I can put something like 0 then 0. So oops, yeah, this is going to be just an origin point, And then I'm going to give a different coordinate for the second point of my polygon. This is 1, 0, and so it goes. So I'm going to create a number of points, and here you can see that I'm not restricted with the number, because I can use like a variable number of poles in my polygon. And I can also like take advantage of this simple syntax. You see that I have this pair which denotes one point, and then I put them all in a set, in a container, and this container is sorted, and this way I can declare my polyline, my polygon very, very easily. So here we go, and now I need to process this initializer list in my constructor, and for that I'm going to decide basically what I'm going to have internally, what I'm going to store in my simple polygon in order to return segments and poles by request. And these three methods, I'm not going to call them myself, they will be called by this interference polygon 2D tool. So let me decide on that, and basically why not just to store all the poles of my polyline in a container which is std vector, and here I'm going to put this gp pnt 2d. So let it be just m poles. These are the poles, these are the control points, let's say, of our polyline. Alright, so now what we need to do, we need to convert this initializer list to this vector of poles, and for that I'm going just to run this range iterator like const auto, then poles, and now what I need to do, I need just to push back poles, and then push back. I need to push back a pole here, and here I need to construct this gp pnt2d, so let's do that. I'm going to construct one point here, let's call it just p, and then we can take like pole, and pole is a pair because I am iterating here with initializer list, which is a sort of container, and at each iteration I'm getting this pair, and to access the coordinates I just need to go like pole first and then pole second. So here we go, we have this point here, and then I can push it back to my poles collection. Alright, so now we have this collection initialized, and basically I'm kind of ready to implement these methods. And for the number of segments, what I need to do, I need just to okay, if I have two poles, then it means that I have one segment, right? So I need to return something like poles, then size. For one segment it's going to return 2, and then I just subtract 1 from here. And let me also convert it to integer, because here the type of the return value here is size t, which is not int, and in order to avoid any compilation warnings I want to convert it explicitly to integer. And now return. So here we go. For a polyline of 3 poles we are going to have 3 here, minus 1 is going to give us 2 segments, which is exactly what we want to have. And this is an accessor. So here we are provided by the index, which is a 1-based index, and we are supposed to return the starting and ending points. So for that we can simply go like poles, then the index. I'm not quite happy with there. Let's call it just maybe, I don't know, index minus 1, because the indexation in the vector in STL collection is 0-based, it's not 1-based as an OpenCascade. And here I'm going to initialize this begin and end. So then here is a deflection. Okay, in OpenCascade, whenever you do not know which deflection to use, you can start from what is called precision confusion. So it's like a standard minimal distance between 2 points. So let's just return this precision colon confusion. This is a reasonably small value which we can use if you do not know which deflection to use, and if you do not care about deflection. As long as it works, we do not care about it. Okay, so we have this polygon implementation, and it seems to me that right now we are ready to construct a couple of polygons, right? So for that I'm going to give some meaningful coordinates here. And now we can pass them to our algorithm here, like this. And actually the computation of interferences will be done right away. It will be done in Constructor. If you do not believe me, you can just go and find the implementation of this tool here. So what we can see that, okay, if we are not using this default constructor, if we are using this complete constructor, what's going to happen is the first thing it checks that bounding boxes of these two polylines are not completely outside each other, which is quite reasonable, and it's an essential thing to do whenever you are looking for some intersections between two geometric objects. And then you see that if it's not like this, if these bounding boxes intersect each other, then we can call this interference thingy here, and here actually you have this implementation. It's quite isolated. It doesn't employ any sophisticated math, but it's still quite something which you might want not to implement by yourself, because it's still a bit laborious to implement it, to come up with such a sort of a thing by yourself without employing some proven algorithm. And I can say that this algorithm is well proven. It works nicely, it's quite efficient and robust at the same time, so I would recommend you give it a try whenever you have this problem of whether your polygons are intersecting each other or not. So let's come back to our exercise. Right now we have this interference polygon tool initialized with our two polylines, and now we can ask for the result, and for that I'm going to ask something like number section points. Yeah, so this is going to return just number of intersection points, num points, which we can output. And that's basically it. So let's go ahead and try to run this exercise. You see that right now we do not have any visualization, and we just want to check that the algorithm itself works. So you see that it compiles. In my case, I'm going to put a breakpoint here just to trace its execution in runtime, and let's see what's going to happen. Alright, so you can see that if I go inside this constructor, I arrive shortly here. I have this initializer list. You see that it has this size 3, and it contains the pairs of my coordinates, so it's quite explicit in Visual Studio. And then we iterate and construct our GP PNT2D points, and we end up with having this field of M poles initialized. You see that my coordinates are all here. And the same way we construct the second polygon, and then we run this algorithm, and then we see, okay, there are no intersection points. So it seems that we do not have any, because maybe these coordinates are not good enough. And in order to see that, in order to check that, I want to plug in some visualization facilities in there. And if you remember, in one of the previous lessons we plugged what is called AIS, which is Application Interactive Services of OpenCascade, and here we are going to make use of it. The only problem with AIS is that it's all about shapes, and so far we do not have any shapes. We just have a couple of polylines, And even worse, all our polylines are not, native OpenCascade types. Of course, we inherit something from Intf package, but this Intf package is kind of isolated math package. It doesn't know anything about shapes and even geometric entities, and that's why we cannot visualize our derived classes, and we need to do something. We need to construct, we might want to construct a shape from this polygon just in order to be able to visualize it with AIS. So let's go ahead and try to do something like that. And for that I'm going to use like a trick. So what I'm going to do, I'm going to convert this polygon to a shape, to a wire. And for that, let me declare conversion operator, which is going to convert my polygon to a shape. So you can do it like this. A bit of C++ magic here. So what we want to construct, we want to construct a wire or a loop or a contour containing our polyline. So here I'm going to use brep builder API make polygon, and I think I have to include it in the first place somewhere here maybe. So there we go, and now I'm going to iterate over this container of my poles with a range iterator. So it's going to be just const auto, then p, then m poles, and then mk poly add, I think. We need to add the coordinates of this point here, but we cannot simply do that, because if you check the interface of this make polygon thingy here, you see that it doesn't accept GPPNT 2D. It accepts rather GPPNT, and GPPNT is a three-dimensional point. And we do not have three-dimensional points, we have only two-dimensional points. And that's sort of a problem, but it's actually like a design problem. And what we need to do, we need to convert, we need to map this. We need to map these two-dimensional points to a three-dimensional points. And for that, the conventional way of doing that is to select a plane. You might think of this plane as of a sketch plane, or your drawing plane. So if we had a plane, then we can simply like drop a point, a two-dimensional point onto this plane, and then we can use the corresponding point on the plane, which is going to be a three-dimensional point. So let's go ahead and declare some plane which we could use. So I'm going just to do it in a simple way. You might want to do it in some other way, but why not just to declare my plane as a static member field of my polygon, and I'm going to have this geom plane. It's a handled instance, it means that it's a shared instance, it's a smart pointer. And I'm going to have like a plane here. I need, I think, to include it first. So there we go, we have a plane. And the first thing I do, I kind of initialize it. But before that, what I have to do also in C++, I think, in order to avoid having any linker problems, I need to also declare it here, like this. And then somewhere in my main function, I can select a plane which I'm going to consider as a drawing plane in my code. And this is going to be new geom plane, and why not just to use X or Y as a reference plane. So we have this plane right now, and then once we have it, we can actually go ahead and map this two-dimensional point to three-dimensional point. So for that, what I'm going to do, I'm going to just take this plane and compute its value in U and V coordinates. and u and v coordinates will correspond to x and y coordinates of my two-dimensional point here. So I'm going to do something like this. So here I treat my two-dimensional point as uv point in the coordinate system, in the local coordinate system of my plane. And that's kind of enough. I initialize my make polygon tool, and then once I'm done, once I have all the points collected here in this tool, I can go ahead and just return this mk poly, then dot, then shape. And this is something to construct our contour, our shape. We have this method of conversion in our polygons here, and now we can initialize a viewer. Somewhere in the end I have to go and call something like start message loop in order to start interaction, and this is a blocking call. It means that once I'm here, I'm not going to proceed to the next statement until the window of the viewer is closed. So there we go, we have this v out, and now I can go ahead and just add my polygons to the viewer. As simple as that. So you see that I do not even need to convert my polygons to a shape, because this is going to be done implicitly thanks to this conversion operator. Now we can have a look at our polygons, and you see that I do have some polygons here. And actually I do have a couple of intersection points. You can easily notice that these two polygons intersect each other, and I am supposed to have like 4 points, 4 intersection points, but for some reason I am not having any. And you see that the result is still 0, surprisingly enough. So in order to see what the problem is, what we can do, we can just debug a bit this interference polygon 2D tool, because maybe there is some problem in this derived class, and maybe there is something we are also supposed to do, but maybe we just forgot to do something. So let's go ahead and put a breakpoint here, and I'm going to eliminate these 2 breakpoints. Alright, so let's step inside this tool. This if statement here is supposed to check if the 2 bounding boxes of my polygons do not intersect each other, because if they do not, then there is no sense to go for detailed intersection and to find these intersection points. And you can see that this check actually, this condition here returns true. It means bounding box of my first polygon is out of the bounding box of my second polygon. And this is actually strange, and we can get back to this check once again and step inside. Yeah, and you see that there is in my Intf polygon 2D, which is a base class for my polygons, there is this field which is my box, and I'm pretty sure that this my box thingy remains uninitialized. So we can go ahead and watch it. And you see, this is my box, and all the coordinates of my box are just zeros. And it means that there is clearly something which I'm supposed to do about this my box. It's not explicitly declared in the interface of the tool, but we can find it out by ourselves. And actually here, when we construct our simple polygon, what we have to do, we have also to initialize this my box. So my box is the thing, is a field which we inherit from this base class. So what we have to do, we have to add this point, which we have just constructed out of our pair of coordinates, to this bounding box, because otherwise, if we do not do this, this box is going to remain uninitialized. So let's see if it's going to fix the problem. I'm going to compile and run this whole thing once again. So if we go inside this interference polygon tool, you see that now this statement here is true. And it means that, okay, you see that this is a tolerance which we use. We grab this tolerance from the two polygons. It's pretty clear that the meaning of this tolerance is accuracy of your polygon. Like if you do not have very precise polygon, if you have some, near coincident but not exactly coincident points in your polygon, then you might want to increase the value of this tolerance. And now you see that it all executes nicely, and I have my 4 intersection points. So the only thing which I want to have as well, I want to visualize them, because I want to be sure that these 4 intersection points were detected, correctly, so I have them right in place. So for that, I'm not just going to grab this number of intersection points, but I'm going to iterate over the found intersections. So for that, I'm going to run another loop, and I'm going to have this index of solution from here. As usual in OpenCascade, it starts from 1, and it's going to iterate all my intersection points up to this num PTS number here. And let's increment the counter. Here we go, and the intersection point itself can be grabbed from the algorithm. So somewhere here we can find this PNT value or PNT2D value. So I'm going to grab this PNT2D value because it's a point in 2 dimensions, just like our polygons are specified in 2 dimensions. So the intersection point is living in the same 2-dimensional space. So we are going to grab it like this, and it's going to return this GPPNT2D, which is a solution point in 2 dimensions. And now if I want to evaluate, if I want to have like this point in 3 dimensions, then what I can do, I can use the same trick. I can use the same plane here and just evaluate this plane using the coordinates of my solution as u and v coordinates. So the only thing here is that I need to use this namespace. Yeah. So yeah, this plane, once it is evaluated, it returns a point which is now a 3-dimensional point. Let me call it like so, 3D. And now I want to visualize it, and again, in order to visualize it, I need to have some topological entity, to have some either vertex or face or edge or something which I can pass to AIS services. And for that, I'm going to use this vout, and then I just go and construct a vertex right away, which is going to be brep builder API, then make vertex, and here I pass with sol 3D. As simple as that. So I just need to go and include this thingy here. There we go. So let's check. Here I iterate over all the found intersection points. For each point I am taking its u and v coordinates, and then I evaluate these u and v coordinates with respect to my drawing or reference plane, and then I construct a vertex just in order to be able to visualize this intersection point in a 3D viewer using AIS services. So let's run it. Okay, you can see that there are some points. If I zoom in, yeah, you see that I have all my points successfully detected. So I think that's it for today. We have learned how to use this interference polygon 2D algorithm. This is quite useful tool, especially if you are doing a lot of computational geometry stuff. I mean, of course, if you have like tons of polygons which you want to intersect with each other, maybe this is not going to be just the best solution possible, because in this implementation, for example, if you construct a simple polygon like this, when you are going to have some dynamic memory locations here, for example, because we have a vector of coordinates. But you can start from this implementation, you can see how it works and if it suits your needs. I hope this lesson was useful, and feel free to post any questions and comments. And also I invite you to join our forum at analysiscitus.org. Here you can always ask whatever questions you have regarding implementation of engineering software, and chat with other colleagues and other people who are quite advanced in all this computational stuff and computational geometry and geometric modeling. So have fun with the library and see you later.